Hello, these are practice problems for symbolic questions in AP Physics. The difference between a typical problem and a symbolic problem is that your answer will not necessarily be simply a number. So if we look at this example that we did in class, we'll walk through it once more. A certain volcano on Earth can eject rocks vertically to a maximum height h. Before we go any further, I'm going to draw my little volcano here. Ooh, there's my volcano. And it can shoot this rock straight up. That's what it means by vertically. And it will go to some maximum height. And this is on Earth. So that means we know a lot of different things about what's going on with this rock or these rocks. We know that at the maximum height, they have a final y velocity of 0. They have gone up some height h. And we know they have some initial y velocity. And amongst all of this, we know that it has a negative acceleration, which is just, we'll say, negative 10. So we know all of this information simply because it says it launches something vertically on Earth. So let's organize this information, just like we would in a kinematics problem. Since it's vertical kinematics, we'll start with delta y, which we know is height, capital H. We know v initial y is there. Well, it's unknown for us. I don't know why I'm writing a 3. We know that our final y velocity for this is 0. And we know that our acceleration is just negative 10 meters per second squared. So our time is also there, but we're not going to spend much time with it because, as you'll see in a second, we don't actually need that information. Now, to actually go on and read part A, it asks us how high these rocks would go if a volcano on Mars ejected them with the same initial velocity. And the acceleration is different on Mars, as it says right after that. It's 3.71 instead of 10. So, before we get to Mars, however, we need to know what's going on with the same initial velocity, because we do not know the initial velocity. So, to begin with, we're going to use the 3 things we know: displacement, final velocity, and acceleration, to find our 4th unknown, which is this equation right here. I'm sorry, the initial velocity. And so which equation do we need in order to find that initial velocity? We have displacement, 2 velocities, and acceleration. If you are thinking the 3rd kinematic equation, you are correct. So final velocity squared equals initial velocity squared plus 2 times acceleration times delta y. So, in this case, I can go ahead and substitute in things just to make it a little simpler. My final velocity is 0. 0 squared is 0. My initial velocity is what we're looking for, so we just have initial velocity squared. We have a 2. We have negative 10. And then we have delta y, which is just capital H. So let's simplify this. 0 is equal to v initial y squared minus 20 times h, and we can rearrange this and just say that v initial y squared is equal to 20 times h. Now I'm going to leave that alone for right now. You are welcome to, if you want to, go one further step and say v initial y equals the square root of 20h, but as you'll see in a moment, we don't necessarily need to do that. So now let's go on and look at part 2, where we're on Mars. So on Mars, we now will be launching the same rocks, but we don't know how high they will go. So now we have a new unknown delta y. We know the initial velocity, but it's a symbolic velocity, so we can say that that is square root of 20h. We know that we're still launching rocks, and we want to know how high they'll go. So our final velocity is still 0. It's the same setup, just a different acceleration. And the acceleration on Mars is going to be negative 3.71 meters per second squared. And again, time is just kind of there. And so now we're going to go in and we're going to find our unknown, given 3 things we do know and 1 unknown. And it's the same equation that we can work with. So again, v final squared equals our initial velocity squared plus 2 times acceleration multiplied by delta y. And so start plugging things in. So our final velocity is again 0. Our initial velocity squared, oh, we have that right above us. So our initial velocity squared is just 20 times capital H plus 2 times negative 3.71 times our unknown delta y. So let's simplify this. 0 equals 20 times h, and then 2 times negative 3.71 is negative 7.42 times delta y. So now I'm just going to solve this for delta y. So I'm going to subtract 20h from both sides, equals negative 7.42 times delta y, then divide by negative 7.42. Let me use a different color to indicate that. And so my final delta y in this case will be 20 divided by 7.42, which is 2.7 times h. So my final answer here has a number in it. However, it is also in terms of h. So now let's take a look at part B. B asks, if the rocks are in the air for a time t on Earth, how long, in terms of t, would they be in the air on Mars? So in order for us to talk about how long they're in the air, we know that that's going up and coming back down. So for B, what's really important here is that delta y is actually 0. We don't need to worry about this h business. So let's go over and take a look at B. And so for B, we have a delta y of 0. So it says we have time t on Earth. So on Earth, let's actually figure out how long this capital T is. So we know delta y is 0. We know our initial velocity is square root of 20h. Okay. We know that our final velocity technically is going to be the negative that because of symmetry. But let's see if we need to use that. Our acceleration is negative 10 meters per second squared, and our time is just capital T. So let's see if we can figure out that T. Now, this is not going to be super easy, but if we go and look at the second kinematic equation, so delta y equals v naught yt plus 1/2 ayt squared, and substitute in everything we know. So we have 0 equals square root of 20 times h. Now, instead of little t, we have capital T plus 1/2 times negative 10 times capital T squared. We have an equation that's not too bad. So we can do two things here. One, I'm going to simplify this. This is just negative 5. And then I'm going to factor out a capital T. So I factor that capital T out, and I'm left with square root of 20 times h minus 5 times capital T. And so I get two answers from this. One, t is equal to 0. That's the first time I'm at this height. That's easy. That's when we started. And the other comes from square root of 20 times h minus 5t equals 0. So now I solve for that capital T. So I have square root of 20h equals 5t, or t is this kind of ugly, let's say square root of 20h over 5. Okay, well, that's not too pretty, but we can work with it. So now let's go over to our Mars and see how it's different. So for Mars, we have delta y is still 0. Let's actually scoot over so we have a little more room. Delta y is still 0. V initial y is square root of 20h. Oops. Same initial speed. V final y should be the same, just negative. Our acceleration is different on Mars, however. It's negative 3.71. And now our time is unknown. Okay, so going through the same process. Let's see if we can avoid using this final velocity for now. So we're going to say, all right, delta y equals, from our second kinematic equation, v naught y times t plus 1/2 ay times t squared. Now here I'm just going to be solving for little t. So delta y is 0, v initial y is this ugly root 20 times h, times little t, plus 1/2 times negative 3.71 times little t squared. And so I'm going to do the same thing I just did, where I'm going to factor out little t from both terms, and I'm going to simplify this right here. So I have square root of 20 times h minus 7.41 times little t. So again, I get two values for t. T equals 0 is not helpful to us. The other comes from saying root 20h minus 7.41 times t equals 0. All right, well, I get something that's really ugly here. So I'm just going to go ahead and skip to it. And that is root 20h over 7.41 is equal to t. So now, how do I translate this in terms of big T? Well, it's actually not so bad, right? All we really have to do is we have to multiply by a factor that translates this to t. So basically we're going to say there is 1t, so use it like a conversion factor, per square root of 20h over 5. So this is the denominator here. And what you see, hopefully, is that this square root of 20h cancels out, leaving me just the statement that little t will be equal to, so move this 5 up to the numerator because I'm dividing by a fraction, 5 over 7.41 times big T. So if we simplify this, we'll get our answer. 5 divided by 7.41 is 0.675 times t. So we found the time in terms of big T. It is not very pretty. However, most problems that you see that are symbolic will not be this ugly. And you'll see that in our other example problems. But overall, we get some ugly numbers because of this 3.71 that we're working with for Mars acceleration. So if you made it through this entire problem, give yourself a high five, take a break before you move on to the next one. All right, now looking at number 2.75, we have two stones that are thrown vertically upward. Again, we're throwing vertically upward. One with 3 times the initial speed of the other. So let's sketch this out real quick. So here is stone 1 and stone 2. So 1 and 2. And so stone 1, we'll just say is our first stone, and it has an initial speed of v naught y. And stone 2 has a greater initial speed, which is 3 times v initial y. So it's the same v initial y that we're talking about here, but this one is 3 times the initial speed of the other. So you know what? Let's actually say that these are just thrown up with a speed v initial, so that when we go in and we talk about these two stones, we can talk about them a little separately without using a huge amount of subscripts. So if the faster stone takes 10 seconds to return to ground, how long will it take the slower stone to return? So let's take a look at A together. So we know delta y in this case, so it's going up and it's coming back down, is 0. We know the initial y for, let's say, stone 1 is v naught. But let's actually work with the second stone first, since it's asking us, or tells us that it takes 10 seconds for the faster stone. So v initial 2 is 3 times v naught. Now our Vy is technically unknown, but we could say that it's negative 3v initial. Our acceleration is just from gravity, so negative 10. And our time for this first stone is 10 seconds. So let's not use our final velocity here. And let's go ahead and use our other information. Now, why do we need this information? We can find something about v initial. So how do we do that? So, in this case, delta y equals v initial y times t plus 1/2 acceleration times t squared. So let's substitute in the stuff we know. Delta y is 0. V initial y is 3 times v naught. T is 10 plus 1/2. Our acceleration is negative 10. And t again is 10. Don't forget to square it. Let's simplify what we wrote. This is now 30 times v naught minus, so let's see, this is 5 times 100, so 500. So now we actually have our v initial, which is just going to be 500 over 30. Let's just leave that as it is for right now. And so when we go back into this, so we're going to now go for stone 2. So our delta y is still 0. Our v initial y is now just v naught, which we know to be 500 over 30. Our vy we're not going to worry about. Our acceleration is still negative 10. I'm sorry, this should say ay, I'm sorry. And we want to know our time. So we're not going to use vy here. So let's see if we can use the exact same equation. So delta y equals v naught y times t plus 1/2 acceleration multiplied by time squared. And what we know is delta y is 0. V naught y is 500 over 30 multiplied by t plus 1/2 times our negative 10 acceleration times t squared. So, quick little simplification. So I can factor a t out of this right-hand side. So I have t, and then I have left over 500 over 30 minus 5 times t. So to solve for this, I get two different times. The first one is very easily t equals 0, right? That's when I start at this height. And the second one is going to be 500 over 30 minus 5t equals 0. So I have 500 over 30 equals 5t, or t is equal to now 100 over 30, which, if we just calculate that as a decimal, is 3 1/3. So 3.3 repeating. So it should take us 3.3 seconds to return for the slower block. Okay, now taking a look at B. The slower stone reaches a maximum height of h. How high will the faster stone go? So let's take a look over at part B. So let's draw a line to separate here. Separate our two parts. And let's start working on B. So for B, what has changed? So now delta y is technically unknown. It's h. It's some maximum height h for our stone. So this is actually the slower stone first. All right, we're doing the slower one first. And so our initial speed in this case is just v naught, or 500 over 30, which let's go ahead and make that into a decimal. That's 16.7 meters per second. We now know we want to go maximum height, right? So maximum height. And what that does for us is it lets us say that our final y velocity is 0, and our acceleration, as always on Earth, is -10. And we don't actually care about time, but for completion's sake, let's put it there. And so now we have these 4 things that we can use. So now let's go back to that third kinematic equation. Vy squared equals v naught y squared plus 2 acceleration times delta y. So what are we going to get from this information? We're going to get an approximate value for h that we can use to translate our faster rock's height into something in terms of h. So Vy is 0. V initial y is our 16.7 squared plus 2 times -10 times capital H. So let's go ahead and do this. So I'm actually going to plug in 16.666667 squared, just so you're not confused if I get something slightly different. So this is approximately 278, we'll say, minus 20 times h. So now we're going to solve for h. So we add 20h to both sides equals 278. H is pretty much 13.9, and that's meters. So we've figured out in meters how high the slower rock goes. Now we need to translate this over into the faster rock. So the faster rock is going to have an unknown delta y. I don't know how high it goes. It's going to have an initial speed of 3 times v initial. So that's going to be 3 times, actually if we write this as 500 over 30, that makes our math a little easier because that makes this now 5, 0. Right, because our 3's cancel and it's 500 divided by 10, which is just 50 meters per second. All right, our final velocity is still going to be 0, and our acceleration is going to be -10. And our time is unknown. We don't need it. So now we have these 3 things. We can go to our third kinematic equation once more. So v final squared equals v initial squared plus 2 times acceleration times delta y. And so we're solving for delta y in this case. So we plug in our 0 squared, 50 squared, plus 2 times -10 times our unknown delta y. So now we know that this is 0. 50 squared is going to be 2,500 minus 20 times delta y. So if we now add 20 times delta y to both sides, that's equal to 2,500. And so our delta y is going to be 125 meters, but we need this in terms of h. Okay, so we just need to convert. So we have 125 meters, and we have h per 13.9 meters. So basically we're just dividing 13.9 meters into 125. And when we do that, we get pretty much 9h. So the height the second one goes is actually 9 times as high. So let's actually make a little bit of sense of this. What we're meant to notice here is that if I have 3 times the initial speed, it will take 3 times as long to come back down. Okay, so 3 times the initial speed compared to some initial speed will give me 3 times as long in the air. Then when we're talking about height, 3 times the initial speed actually gives me 9 times the maximum height. So there you go. A little bit of interesting knowledge that we get from trying to work with symbolic problems.